Today, I'm going to show you how to start analyzing your game scene so you know what needs to be optimized. Let's go. So we're in the middle of a series of videos on game optimization. Last week we talked about choosing your target hardware and frame rate, and then setting budgets. These are pretty critical topics, so if you missed last week's episode, I'll link it down in the description so you can catch up. We also talked about finding locations where your game is not hitting your target frame rate. Once you've found these problem spots, it's very important that you analyze them to figure out what's causing the game to run slow. You have to find the cause first before you just blindly start trying to fix things. If there's only one thing that you learn from this entire set of videos, I hope that it'll be this: analyze first, then optimize. If you just start blindly trying to fix things without finding the source of the problem, you may end up reducing the quality of your graphics without actually making any difference in performance. I'll explain how that can happen in a minute. The first thing that you need to discover is, what is the main source of your slow rendering? The game uses two resources to run, the CPU and the GPU. To render each frame, both processors do work. And in order to remain in sync, the processors do their work for the current frame and then wait for the other to complete. The processor that completes its task faster must wait for the other one to finish. This waiting time is wasted processor time and needs to be eliminated so that both processors finish as close as possible to the same time. If you make optimizations on the processor that is already finishing faster for each frame, frame rate will not improve because it will just mean that that processor is waiting longer for the other one to finish. Successful optimization always starts with determining which processor is finishing last, and then performing optimizations that specifically target what that processor is doing so you can close the gap. We call this being CPU bound or GPU bound. If your on-screen metrics include a CPU time and GPU time, it's easy to see if you're CPU bound or GPU bound. Whichever processor has a higher time is the one that's bottlenecking the scene. If your metrics don't include these two stats, it's very easy to figure out the source of the problem by just following these steps. First, build your game and run it outside the editor. Like we talked about last week, performance analysis is most effective when it's done in a standalone build because the editor introduces some overhead that can give you incorrect results. Next, turn on a frame rate or a frame time counter so that you can see the current performance. Next, temporarily reduce the screen resolution to around 50% of the original resolution as a test. Reducing the number of pixels required to render will significantly reduce the workload on the GPU. You don't want to leave it that way, but as an artificial test, it'll help you to see what the performance could be if you reduce the load on the GPU. If the frame rate remains the same, you know you're CPU bound, and you should focus your optimization there. But if performance improves, you're GPU bound, and the frame rate you see is the point where the GPU and CPU are evenly matched. That means if you reduce the load on the GPU, you could potentially get to that frame rate. So let's take a look at how this is done in Unreal and in Unity. Alright, here I am in my scene in the Unity editor, and what I need to do is discover if my project is CPU bound or GPU bound. And so what I'm going to do is do a build of the game and run it outside the editor so that I can figure out what its current performance is. And so I'll just come over here to File, build profiles, and you can see that my game is set up to build on Windows. Now, if I were targeting a different platform, I would want to make the build for that platform. If I was making a project for Android or for an iPhone or something, then I need to set up a build for that. But in my case, we're just going to test this on Windows. And so I'm going to set it up just like you see here. And I can just hit this build button. And then I'm going to run my build and see what my frame rate is. All right, so now I'm running my build outside of the editor. This is a standalone build. And you can see that I'm getting about 82 frames a second, or about just over 12 milliseconds of render time. So this is what my current frame rate is. And in order to discover if I'm CPU bound or GPU bound, I need to do a test where I reduce the number of pixels that I'm rendering. So I'm going to reduce the resolution of the render, and that will cut down the total number of pixels that I'm rendering, and I'll be able to tell if I'm GPU bound or CPU bound. So let's jump back into the editor, and I'll show you how to reduce the resolution. Now, I am running about 82 or 83 frames a second, and that's pretty fast, but I'll also just tell you that my machine is running an RTX 4080, which is a very high-end video card. A lot of people don't have that kind of graphics power in their machine. So even though my frame rate is pretty fast on my machine, if I wanted to render on a much broader segment of the market, I'm probably going to need to optimize it further. And so that goes back to what we talked about last week about selecting your baseline target hardware first. Right now I'm getting a really nice frame rate, but it's because I also have a pretty strong graphics hardware. Okay, well, let's jump back into the editor now. And here we are back in the editor, and the thing that we need to do next is reduce our rendering resolution. So I'm going to come down here to my settings folder, and I'm going to pick my URP high fidelity render pipeline settings. And I can come down here to quality, and I can see this setting called render scale. And I can grab the render scale, and I'm just going to reduce it to like 0.5, which is going to be half the normal render scale. And what that's going to do is it's going to make my build render at a significantly reduced resolution, a lot fewer pixels. And so what I'll be able to tell is if my frame rate improves rendering fewer pixels, then I'll know I'm GPU bound. But if it stays about the same, then I'll know I'm CPU bound. So let's go ahead and build this. So again, I'm going to come up here and go File, Build Profiles, and Build. And now my game's going to build, and I can run it outside the editor. Okay, so here we are running that build. And if you'll remember, we got about 82, 83 frames a second before. And now we're getting 158 frames a second, or about 6.3 milliseconds. It's almost double the rendering speed it was going before, because we halved the number of pixels that we're rendering. And what that tells us is that we are significantly GPU bound. What we can learn from this is if we could somehow optimize what's happening on the GPU, so that we can render at full resolution but still get this speed, this will allow us to close the gap, because right now it's taking our GPU a lot longer to render than it's taking our CPU to do its work. So if we're able to close that gap, then our final result will be a frame rate that's much closer to this, 158, 6.3 milliseconds per frame, and that'll be great. That's kind of what we want to shoot for. And so we know here in this Unity project that our optimizations need to be focused on what the GPU is doing, because if we were to go in and cut out a bunch of things that the CPU is doing, that wouldn't help us at all. We need to focus on just what the GPU is doing in this particular project. Now, in your project, it might be very different. So you can't just follow along and do exactly what I'm going to do. You need to analyze your project and figure out, are you CPU bound or are you GPU bound? All right, so that's what it looks like in Unity. Let's take a look at how to do the same thing in Unreal. Oh, one last thing. You might be asking yourself, how did you get that statistic on the screen? Or how did you get the frame rate and the frame time counters there? Well, that's a setup that I created. And there's a separate video that I made that I'll link down in the description that explains how to set up that frame rate counter and that frame time. So yeah, I'll link that video down below, but that's a separate process to get those statistics on the screen. All right, here we are in Unreal, and here I want to determine if we are CPU bound or GPU bound. So just like we did in Unity, we need to go ahead and do a build of our game so we can run it outside the editor, because the editor does some things to the performance that make it different than the actual build that's running outside the editor. So I can come here to our little platforms drop down, and I'm going to pick Windows, and then I'm going to pick Package Project. And we can go ahead and package up our project outside the editor. So I'm going to go ahead and select it. And now our project is building, and we can wait just a minute. And then we're going to run the project outside the editor. All right, here is our project running outside the editor. And the first thing that we need to do is determine what the performance is. So I'm going to hit the tilde key, which is just below the escape key. And now I can type in a command. So I'm going to come down here to the lower left-hand corner, and we're going to type the command stat FPS and hit enter. And now Unreal has placed the performance in the upper right corner. We can see there that our frame time is right around 63, 64 frames per second. And it's somewhere between 15 and 16 milliseconds of render time. And so we want to determine, are we CPU bound or are we GPU bound? And in order to determine that in Unreal, I can turn on some additional metrics. So again, I'm going to come down to the lower left corner. I'm going to hit the tilde key, and this time we're going to type stat unit graph. And this is going to turn on some key statistics, and they'll be displayed in the upper right, just under our frame rate and frame time. The first statistic there is the frame time, which here it looks like it is just around 16 milliseconds. The next statistic is game, and that is about 1.6 milliseconds. Now game, what that is the amount of time it takes on the CPU to complete all of the work in the game thread. So there are multiple threads in Unreal. One of them is doing the game logic, and that's taking about 1.6 milliseconds there. The next item is called draw, and that is the amount of time it's taking the CPU to prepare and send the draw calls to the GPU, and that's taking about 15 to 16 milliseconds. And then the next item we're interested in is the GPU time, and that is taking about between 14 and 15 milliseconds to happen. And so what I'm seeing here is it looks like in Unreal we may be CPU bound because of the large amount of time it's taking to do that draw item on our list. So our draw calls, maybe the number of draw calls, or maybe maybe just how expensive those draw calls are what are taking a really long time in Unreal. And we could probably increase our frame rate by reducing the cost on the CPU to calculate our draw calls, because that's taking the majority of our time. So now that we understand that, we can jump back into Unreal and see if there's something that we can do to speed up the amount of time it's taking the engine to do those draw calls. Let's jump back into the engine, into the editor, I mean, and see if there's something that we can do to fix that. Okay, so now we're back in the editor, and what I want to show you is just a couple of debug views. Oh, you know what? First I need to change the size of the UI just so that you guys can see it a little bit better. I'm going to come here to debug widget reflector and set this to 2 so that it scales up the UI so that you guys can see it a little bit better. All right, so what we're going to do is come up here under these view modes, and I'm going to drop this down, and we're going to take a look at Nanite visualization. What's happening here is Nanite is sending data to the GPU, but there's a lot of work that it has to do on the CPU in order to prepare that data. And one of the things that we can do is use these debug view modes to see what kinds of things it's needing to do to the data in order to get it ready. So we're going to come here under Nanite visualization, and I'm going to pick evaluate WPO. WPO stands for world position offset. And what that means is that our Nanite meshes, every frame, are evaluating vertex offsets. So something that, if we see any of these that are doing it, it means that something that's happening in the shader is causing the vertices to move out of their original locations. So I'm going to pick evaluate WPO, and we're going to take a look at what this looks like. Okay, now normally if you look at a debug view mode and you see something that's green, you think, oh, that's good, right? And if you see something that's red, you think, oh, that's bad. But in this case, I don't know why they did this, but it's actually the other way around. The items that are green are evaluating WPO, and the items that are red are not. And so what this means is that something is happening in the shader to cause these objects, the vertices in these green objects, to be moved. And I think that this is actually happening on the CPU, that this moving vertices around is being done on the CPU, and that is why our draw time is so high. And so I'm going to pick one of these meshes. Let's see if we can pick one of these meshes here. And let's just jump into the material of this mesh. And then we'll take a look at this shader that this mesh is using. It's called M Smart Master 02. We'll just open up this shader. And we're going to come over here and look. It has this block called MF Contact Shadows. And this block is doing something that is causing our world position offset to be triggered. Yeah, it's happening right here. See how it says get material attributes, and we're getting the world position offset. And then here we're adding these values to that in order to calculate some contact shadows. Well, let's take a look at what our scene looks like normally. We're just going to set this back to lit. And I want you to remember what this looks like. I'm going to skip what this is doing just for a minute. We're going to take the input and just wire it directly into the output so that we can skip this contact shadow thingy that's being calculated here in this shader. I'll save this and we'll switch back to main. Okay, who can tell me what you saw or what you see now that's different? I'm not going to do an A-B comparison because that's a little bit unfair, because when you're playing a game, you don't actually see that. But can you see anything that looks different? I don't see anything at all. But if we come back here to our Nanite visualization, evaluate WPO, now none of our meshes are doing that. And we should see a pretty significant performance increase in that draw stat that we were seeing a minute ago. So what we could do at this point is build the game and take a look at that draw stat and see if it's improved. In fact, let's go ahead and do that. So we'll come here under Platform, and we'll go to Windows and Package the Project. And we'll just go ahead and let the project build. Now that we've disabled that world position offset, and our CPU is no longer having to do all that work to change up the position of our vertices. And let's go back into the build of the game that we're doing and see if our draw stat improved. All right, here we are back in the game, and we need to turn our stats back on again. So I'm going to come down here, hit the tilde key, and type stat FPS, and also hit the tilde key again and type stat unit graph. And now we can take a look at our stats. Our draw time used to be hitting about 16 milliseconds, and now it's less than that. So it did drop just a little bit, and it looks like our frame rate went up just a little bit. So maybe not quite as much as I was hoping for, but it did improve just a little bit. Let's jump back into the editor and see. I think there may be one more thing that we can do to improve our stats. Okay, here we are back in the editor, and once again I'm going to set the debug mode, the widget reflector, to 2 so that you guys can see the UI a little bit better. All right, now what we need to do once again is come up here under lit nanite visualizations. Last time we looked at evaluate WPO. This time we're going to look at pixel programmable. And what this is looking at is there's some extra cost here that we're doing on nanite objects. And we need to take a look at the shader and figure out what's causing this. So in this case, last time we wanted things to be red and not green. And in this case, in the case of the pixel programmable view mode, we want things to be blue and not red. So again, we have these objects that are red, indicating that there's something in the shader that's causing this pixel programmable state. So let's go ahead and open our material again. Here's our material, and we'll open our base shader. And we'll come over here, and here we can see that we're doing pixel depth offset shadows. And this is causing that pixel programmable state to be true. So by changing this value that's coming into pixel depth offset, we're putting some extra cost into nanite that's kind of artificially increasing the cost of our rendering scene. What this is doing, I think, is it's allowing our nanite to be a little bit crunchier. If we turn off the debug view mode again, once again, take a look very carefully at our scene. See if you can see anything or just remember what this looks like. And I'm going to turn this off. Here we have our PDO shadows. And if it's enabled, we're giving it the pixel depth offset value. But if it's disabled, we're just giving it 0. And so what I'm going to do to bypass this is I'm just going to wire this 0 value directly into our pixel depth offset amount. So that we're just never using that value. We're just always setting it to 0. And I'll go ahead and save that shader. And we'll switch back over to our main scene. And come back here to nanite, pixel programmable. And now you can see everything is blue. We've gotten rid of that pixel programmable state. So this should make our nanite cheaper to render now. And so let's go ahead and do a build. And we'll measure our performance again outside the editor. We're going to come down here to Windows, Package Project, and just go ahead and hit select that folder. So now it's packaging up our project again. And we'll be able to see what kind of a difference switching off the Evaluate WPO and Pixel Programmable has done for our scene. All right, here we are back in the editor. And now you can see our frame rate is hovering right around 70 frames per second. We've reduced our draw from about 16 milliseconds down to 14 milliseconds. And our GPU time is just under that, or right around the same. So you can see we've made a pretty significant, almost 10 frames a second difference in our performance. Just by changing a few little things in the shader, you can see that In this particular case, Nanite is really sensitive to that evaluate WPO and also the pixel programmable view modes. So does this apply to your project? I don't know. Maybe it does, or maybe it doesn't. Does this help you? Yes, absolutely. And here's what I hope that you'll take away. You need to check which processor you're bound by before you do any kind of optimization. And you need to target that processor. In our case, we were targeting the draw statistic, which is now like right around 14 milliseconds. And we were able to improve our frame rate because we figured out where the bottleneck was, and we found a couple of optimizations that would help bring the cost of that particular part of the rendering process down. So what does this mean for you? It means you need to first figure out if you're CPU bound or GPU bound, and then target specifically the processor that is taking longer to render. So what we're going to do now is we're going to leave this video here, but next week I'm going to show you a list of things that you can do if you are GPU bound. So if you're GPU bound, we're going to go over this list. We're going to optimize this scene and also the one in Unity. And we're going to see what kind of performance gains that we can get. Assuming that you're GPU bound, this is going to be a couple of things that you can do if that's the case. Then the following week, we're going to take a look at if you are CPU bound. And we'll talk about what you can do in that case. We're going to kind of go through this process slowly because there's so many topics to cover. There's so many different things that you can do, but the important thing to remember is you need to look at your scene specifically and discover what is it that's making your scene run slow, and then apply the things that could possibly help, depending on if you're CPU bound or GPU bound. All right, everybody, that's going to do it for this week's video. Hope it helped, hope it was enjoyable, and we'll see you next time.